Kenneth is a postdoctoral scholar with Professor Don Towsley at UMass Amherst. He spent quite a bit of time at TU Delft. I believe you did your MSc and PhD both.
And a short postdoc.
And a short postdoc with Stephanie Weiner and a lot of other researchers in the Delft area. He also worked with TNO for a short duration, which is an entity associated with TU Delft in the same location, and they do quantum research as well. Kenneth's background is in quantum information theory and quantum error correction. He has done a lot of interesting work on error correction codes and connections with graphs and graph states in general. So he's going to talk about our noise in quantum repeater chains. Welcome. And after this talk, anybody feel free to, if you want to have a separate time with Kenneth, feel free to reach out to him directly. And I believe you are in this 523 office.
Student office.
Oh, you're in the student office. I see. Okay. You also, if you need to have access, there's this 523 office that you yesterday that you access. You can have that for the duration of your stay. Like,
sure. Admittedly, I completely forgot that I worked with TNO. That's a long time ago.
Yeah.
Let's see. So maybe as a heads up, this handwriting that you see right now, it's basically as good as it's going to get. If you can't read something, please let me know, or give any other questions, just interrupt me. I won't be too offended. Yes, let's see. So I will be talking about noise and repeater chains, and specifically in so-called swap ASAP repeater chains. Maybe as a quick recap for people who are not too familiar with repeater chains, the motivation is as follows. We have our good old friends Alice and Bob, and they're separated over a long distance. And let's say they want to generate entanglement between themselves, or they want to do QKD, and maybe they have access to some fiber. It's a long fiber that extends over some distance L. And what happens is that as we send photons over this fiber, the photons will get lost with a certain probability. In fact, this probability will drop down exponentially with the distance. So there's some attenuation length, L attenuation, and it drops down as follows. Well, what this tells you is that if you want to go to large distances, you have a problem. This probability will drop down very fast, and you'll basically never get a photon across. So what we're going to do is we're going to insert a repeater. We still have Alice and Bob, but now they get help from their friend, the repeater. We put it in the middle. The idea is that we're going to establish entanglement separately between Alice and repeater, and between repeater and Bob. And they can do so completely independently. Then when they've generated both links, they can do a swap operation here in the middle to generate entanglement between Alice and Bob. So to already give you some idea of what will happen is that this link on the left between Alice and repeater might be generated before the other link has been succeeded. And so we have to keep it around. We have to store it in memories until the other link has been generated. And at that point, we experience decoherence. And so to give you some idea, this is basically the thing I want to study. We can make the problem more complicated by adding more repeater nodes. And I'll get into more detail how to sort of see what happens in that case. Some motivation for, there's tons of ways one could really implement a quantum repeater chain there. You could do stuff like distillation, you could do multiplexing, you could do nested swapping, you can make it very complicated. But I just am interested in the simplest case, which I'll detail in a bit. And these are these swap ASAP repeater chains. So for this talk, my goal is to understand, well, I'd like to think I already do understand, but to explain to you how we can estimate the average fidelity. I use here these angular brackets to indicate the average. And I'll be making some simplifications during this talk. I will be assuming depolarizing noise. I'll be assuming that the repeater chain is homogeneous. This basically means that all the decoherence parameters, all the success probabilities are really the same. Then a further simplification that I'll get into later is that the end nodes are not noisy. No noisy end nodes. Then I also want to discuss something called cutoffs. I won't go into detail now what these are, but they are a method that allow you to trade off the average fidelity at the cost of the rate at which you generate it. I'll explain this later in the talk.
What is the definition of the average fidelity?
So, okay, I'll get later into more detail and also really like to define this properly. Yeah.
And this cutoff is for lengths, for segments between repeaters?
So I will consider two different types of cutoffs, and I'll explain later on how to implement them or what they're based on. But in general, the idea behind a cutoff is that you want to impose this trade-off.
I mean, you can also select on a certain high fidelity if you want.
Yeah. Yeah.
How many of these assumptions are realistic? Or how many of them are close to it?
That's a good point. So let me write down the next part, and then in the paper, I can actually get away with, I can relax some of these assumptions. But for this talk, this would be a little bit too much. But so, for example, I can consider more general noise models. In effect, I can consider a large, for the paper, which is not out yet, hopefully soon, whatever that means. We can consider a large class of Q-bit polynoise that includes arbitrary Q-bit polynoise. So that's already an assumption we can relax. I can consider the inhomogeneous case. So that's, it's quite a strong assumption to assume your repeater chain is homogeneous because, in practice, you don't get to choose where you can place your repeaters. In practice, your repeaters will also have different parameters. So we can deal with the inhomogeneous case as well. Things just become a bit more messy. Also, I find bounds, analytical bounds for the case of noisy end nodes. So we can also deal with that. We won't get exact results, but we can find lower bounds on that case. And one thing I'll also implicitly assume, and that we can get rid of in the paper, is we can include noisy state generation. But for this talk, I'll assume that this state generation is perfect. But again, we can get rid of this.
So when you say a large class of qubit polynoise, is it something that your qubit is embedded in a larger d-dimensional qubit system and the noise acts on the system, but you don't have access to the other levels of the system? Or
so for the qubit case, the only noise that we can, or the noise that we can handle is arbitrary qubit polynoise. So I don't think that the type of noise that you just described, I don't think we can.
right, I was a bit confused by your use of the word qubit over there.
Yeah, and so one can generalize this to qubit polynoise, a subset of qubit polynoise. I'm not sure if that the type of noise that we can handle includes that.
Right.
I'm still sort of trying to understand what are sort of the physical situations in which you would experience, in which you would have this class of qubit polynoise. That's something I don't understand yet. Yeah. Okay. So I said that our goal is to sort of understand this average noise. And so first, I'll actually sort of formally write down what I mean with this. I'll give this problem statement. And then there's sort of three ways I tackle this problem in a paper. I give exact analytics, and that's also something I'll talk about in this talk. I give a numerical approach. And then there's analytical lower bounds. I won't have time to talk about that. So maybe to give some idea, this is a bit of a generalization of actually your work cycle together with Ashley, where we found bounds on the fidelity of repeater chains. And one can generalize this to include cutoffs as well. But yeah, I won't have time to talk about that today. So let's move on to sort of the problem statement, or maybe first the model that I'm considering. I am going to consider a case where we have 5 links. And for now, we should assume that I'm drawing these dots equidistant. I'm doing a relatively okay job, I would say. We have Alice and Bob at the end. Now, I want to sort of go through a specific instance of how entanglement would evolve as we try to distribute entanglement. So let's say at time t is 1. T is 1, we have these 5 links. And let's say at time t is 1, we try elementary link generation, and maybe only this link is lucky, the 4th link. So time t is 4, we have an entangled link here. In the next step, time t is 2, maybe now 2 links succeed. Maybe the 2nd link succeeds. This link was already here, and now the 5th link succeeds. At the beginning of the talk, I said I was going to focus on swap ASAP repeater chains. And the idea is that,
And Kenneth, your model is that the successes in the previous time steps were held.
Yeah.
With no change in fidelity.
so no, there will be
There
decoherence,
will be.
but we'll get into that later. Yeah.
So between epitaxial 3 and 4, does it have a new link or is it carrying?
Just the old link.
Yeah.
Okay.
Yeah.
So it's not that they have 2 links.
No, so I'm now just sort of tracking these links in time. And so since we're doing swap ASAP, well, this memory here, or this node here now sees, hey, I have 2 links. I better swap as soon as possible. So it's going to swap, and we end up with entanglement here. Okay, let's move on to the next time step. Maybe at this is time t is 2, at time t is 3. We had this link here, Maybe now this link here succeeds. Well, I play the exact same trick. We do a swap here, and we end up with entanglement here. And finally, we're almost there. Time t is 4. This link succeeds. Let me do a swap here and here, and we end up with entanglement between Alice and Bob. So this is an example, sketch of how entanglement could evolve over a swap ASAP repeater chain. Are there any questions about this?
One question.
Sure.
So to Ashley, when every time step you only attempt entanglement across a link if you don't already have an entanglement established, or can you shore up more entangled?
No, so you're assuming a sort of the most basic case where you're very limited in memories.
I see. So just one maybe pair of memories for each link.
Yeah, and it's even slightly more stronger, actually, the condition that I imposed. So for example, let's look at, let me draw an example. Let's say we have, let's say we've created entanglement over here between these 2 nodes. Then in principle, these 2 memories, these 2 repeater nodes are free to generate entanglement over here. Kind of looks like a funny face. So that is something that I won't assume in my model that you will do. You'll attempt elementary link generation, and you'll wait until end-to-end entanglement has been generated.
I see. Yeah.
The idea is, well, there's several reasons. One can lead it to congestion. Maybe now you cannot generate this link until then you swap this guy here. So you can get into the scenario where you get this congestion. That's one motivation. The other motivation is that otherwise it becomes very hard analytically to track to handle.
So if I may guess, this is a good model for the case where you have one so-called faithful memory that does not undergo depolarizing noise or any kind of noise. Like as much as the other memory qubits, so you kind of shelve into that memory qubit, and that's the single link.
I'm not sure if I understand your question. So later on, I will detail how decoherence fits into here. So I'll assume that every time step that you're keeping a link around, you'll experience decoherence.
Right.
I'm not sure if that answers your question.
Right, okay, yeah, I think it's in the side. So.
I have a question.
Sure.
Is there some kind of heralding so that you know that entanglement has been successful between two nodes and to initiate the swap?
Yeah. So for example, when the swap happened here, it needs to know that entanglement was there. Yeah. So I assume there's some process that does this. Yeah.
So you are implicitly then assuming that the time slot length is equal to or larger than the time line takes to travel
Exactly.
the length of that link.
Yeah. So it's the time really that you also get a potential confirmation that the entanglement is there.
So that is that time goes in the denominator of your ring.
Yeah. So I make my life simple by just assuming everything is unitless. I just have a single time step. And,
Oh, that's fine.
Yeah. But indeed, there's heralding.
Yeah.
Okay. We're interested in understanding the average noise. And so to do that, we need two ingredients. First of all, we need to understand the probability that I'll get to that later. Let me sort of give another time. Let me write this down graphically in another way. I can think of the above evolution in the following sense, or just describe it as follows. I had 5 links, 2. And at time t, for example, the first link succeeded at time 3, t1 equals 3. The second link succeeded at time t2 is 2. Third link succeeded at time 3 is 4. Fourth link succeeded at time t. And then this guy succeeded at time t is 2. It's not really, proportions are a little bit off, but hopefully you get the idea. I'm just writing down for every link at which time step it succeeded. And that's in principle enough to sort of characterize what happened in the repeater chain. And let me capture this information into just a single object. I'm going to define a t bar, and this is going to be a sequence of numbers, t1, t2, t3, t4. And in general, this will go up to n if I have n links, but in this case, it just goes up to 5. So for this specific instance, I have 3, 2, 4, 1, 2. Any questions about this? So what this T bar really indicates, it indicates a specific instance of me running this protocol. So since I'm interested in the average noise, I should first maybe understand the probability of seeing such a T bar. Well, let's first understand maybe the probability of seeing Ti, which means seeing the ith link succeeding at some time Ti. Well, elementary link generation is a geometric distribution, or corresponds to a geometric distribution. And that is given by the following. And I can rewrite this as follows, where I now define Q is equal to 1 minus P. So it's really the probability that I fill. And I'm going to write this a bit more conveniently as follows. Just pulled out the Q factor. So this gives us the probability of seeing a single link succeeding at time Ti. So that tells me that the probability of seeing a T vector, well, there's just a bunch of independent geometric distributions. So I should take a product over those. This is just equal to, where I pull out this sort of constant factor. And now since I have a product and I have an exponent here, I can just put it in the exponent. So now q to the power the sum over all these TIs. Any questions about this? Okay, this gives us the probability of seeing such a T sequence. Let's now try to understand the corresponding noise. So let me first maybe explain my noise model. I am going to parameterize my states with the parameter lambda bar. The idea is that my states are always of the following form. I have some maximally entangled state, psi, with probability lambda bar. And then with probability 1 minus lambda bar, I have the maximally mixed state. This corresponds to depolarized maximally entangled states. And again, in the paper, we can make this model way more general, but let's stick with this one. This is a very useful parameterization. Why? Well, let me write down some facts. First of all, the fidelity of such a state is given by lambda bar plus 1 minus lambda bar divided by 4. And so in particular, if I want to know the average fidelity, it sort of suffices to understand the linearity of expectation, suffices to understand the average lambda bar parameter. What is nice also is that when I swap two states of such a form, then I go from, so I have two states, lambda bar 1 and lambda bar 2. If I swap them, I get a new state where now the lambda parameter is given by the product of the two. So that's sort of nice. I don't have to do anything fancy. I just multiply it. And finally, if I have some parameter lambda bar and I apply some depolarizing with parameter lambda, then my new parameter is just given by lambda times lambda bar. So everything is just basically multiplication. And I like to think that multiplication I still sort of understand. So this is why it's this convenient representation.
Are you going to be including distillation?
No,
No.
no. So one could say okay, maybe in like a single time step, I try elementary link generation and I try this a number of times, and then I do distillation.
And your lambda takes into account all of this.
Yeah. So one could include that.
Yeah. And this lambda bar is a per time step.
So the lambda bar here is really the value for a single state, and we'll now sort of try to understand how this parameter evolves as we go through this.
Oh, so this is at the step that the state is created. This is the initial state.
So the lambda bar is really just the parameter for any state, because my states will always be of this form.
No, yeah, that I know. So in the time instant where a link is generated across the link, what is the lambda value that you start out with? Is that notation for that?
Yeah. So in this talk, I'll be assuming it's perfect.
Oh,
But in the paper, we can actually deal with the case of noisy state generation.
you will assume it's perfect, and at every time step that it waits, it gets hit by
Exactly.
a lambda by 2. So that's all.
Exactly. Yeah. Yeah. The idea is that since this swapping and weighting, it all corresponds to multiplication, the noisy state generation just becomes a constant multiplicative factor. So it's very easy to deal with. But for simplicity, I will ignore that for now for this talk. So like that said, what is really relevant is the waiting time. You need to check how long is each memory waiting. Well, let's have a look at this memory here. Oops. This memory here. It's waiting until the other link on the left-hand side has been generated. So it's waiting until this time here. Same thing with this memory here. At time t is 2, it needs to wait until this link has been generated, and etc. here. Then finally, Alice and Bob also need to wait until they have end-to-end entanglement. So that would have to be until here, because that's the point where the last link has been generated. As I said in the beginning, I will ignore noisy endnotes. And well, let me sort of motivate this. First of all, we can't deal with this sort of in the paper by giving bounds. On the other hand, one can maybe also assume that Alice and Bob have a lot of resources. Maybe they are doing like error correction on the qubits to protect them against the noise. But maybe a better motivation is to say, well, maybe you're interested in doing QKD. In that case, actually, Alice and Bob don't need to store their entanglement. They can just, after they've succeeded, they can just measure out immediately. So in that case, there's no noise anyway. So for the purposes of this talk, I'm gonna ignore this noise here. And we just have to focus on basically these lines here. Well, a single memory I, has to wait for a time that's equal to the time difference between adjacent links, which is given by the absolute value of their differences. And so the associated decoherence that's experienced is basically just lambda to this power. And since we really have a few of these memories, the total decoherence parameter is really just this guy. I sum all these absolute value differences, and I then take lambda and raise it to that power. And so this really gives me the lambda parameter of the end-to-end entangled state. Any questions about this?
Wait a second, I'm trying to, why did they not add? So lambda to the T1 minus, so that T1, Ti minus Ti plus one, that will probably have what? That will have, what's the distribution of that? It's difference between two geometries.
Yeah, so yes.
Some exponential like distribution.
Yeah, exactly.
Discrete exponential distribution, right?
Yeah.
So, and what is the interpretation of the lambda to the sum of the Ti, those differences?
So the sum of these, so an individual term in the sum corresponds to the time memory I has to wait.
Yes.
And so now the memory gets hit with a decoherence parameter lambda to the power of the waiting time.
And why are they independent random variables?
So there, I haven't said anything about it specifically about how this is distributed.
Oh, you're not, okay, you're just right. This is still a random variable or random vector.
Yes, this
You will write the
corresponds.
distribution of this thing. Okay, then it's
Yeah,
okay. It's
yeah,
fine.
yeah. This is the decoherence for a specific instance.
Got it.
So let us now calculate the lambda, the average lambda intent. And this is going to be the sum over all possible instances, which we characterize by these T sequences, times the probability. Well, if we go up here, we know that's given by this quantity here. So let me just write that down. And in fact, let me just pull out that constant factor. So we had this 1 minus q divided by q to the power n. There's nothing really interesting happening there. Then we have q to the power sum over the ti's times lambda. Oops, that should be a minus. So maybe to be clear, the sum is here from I is n to n minus 1. I is 1 to n. Right. So really, if we this constant factor in front is not too important. So we just want to understand this sum right here. Let me call this Z. Basically, understanding the sum or evaluating the sum. If we can do that, then we can evaluate this average lambda parameter and thus understand the average fidelity. So that's sort of the whole, well, building up to this, the whole talk. This is the goal. Are there any questions about this? All right, then let's move on. So first, I would like to discuss sort of the analytical approach, and what I'll do is I'll phrase this problem recursively. And to do that, I'll need to make another definition. Yeah.
You're not associated with swap.
So I can include noise for swapping because I know how many swaps I'll do. So they'll add a constant lambda factor. So I could also include that.
Just the one multiplicative factor at the out.
Like, so if I'm swapping something early in the like some two nearby links in succeeded and I swap it, is that link more prone to errors than a single link? Like say you wait for a long time.
No, order doesn't matter.
Or
Yeah.
so I mean like these links are farther, right? Like now this is a long link.
But
But
once
it's-
they are established, they are held in the memory. So only the memory properties.
So there are no physical flying photons between that link. It's just qubit of ith repeater and I plus kth repeater are entangled to one another.
Yes, but should I imagine they are
So I think the mental model you can have is, imagine even though Kenneth wants to, I mean, what he's doing is swap ASAP. The mental model you can have is that you wait until all the links have one success, at least one success. Okay, so there will be different waiting times. And then also different fidelities because they got created, somebody who got created in the third step, they'll have higher fidelity than somebody who got created in the second step. And then when you have all the successes, you do swap. So you can keep that model in your mind. So then what he's saying is that there can be a mu to the n-1 that you can pull outside and that can multiply that 1 minus q over 2 to the n.
So this also makes sense to swap as service. So
It is same as swap.
So
Exactly.
I was thinking like maybe a swap as can have other implications because the link is long.
No, because the picture I said is equivalent to swap.
Single link or a long link has the same memory loss.
No, you are accounting for the fidelities. Like, so the fidelities are being accounted for the different lambdas getting applied, depending on when they got successful. But ultimately, the picture is that you have a bunch of links of different fidelities and you do swaps at each point. And now one could say that the swaps can introduce some extra infidelity, but it's just some constant raised to
I
n.
think I understand that.
So there's nothing else about long links versus short links.
Yeah, I think what is it?
But then the initial point was that Alice and Bob are far apart, and then the entanglement goes with L.
So that's the rate, the probability at which you can distribute these things. So the idea is if you're a very long distance, it's not so much that our states will be bad. It's more that we will basically never get a state.
Yeah.
Because my photon will never arrive.
It is.
Yeah. Okay, let me define a new quantity. So we had the Zn, which was the total sum. Let me now define Znt. And it's basically the same thing as before, but I'm only going to sum here over all t sequences such that the last link, Tn, is equal to t. So this is sort of now, I don't sum over all possible sequences. I only sum over those sequences that have exactly t. Let's see.
General swap policies. Distribution.
In principle, one could do that. I'm not sure how much of the techniques that I use really generalized in that case, because I am really using very specific properties of this policy.
But the equation that you have written, Zn of t, is independent of the pi's distribution. Like this is in general how we would write the average fidelity or degree quantity here.
Yeah, that was exactly my point. I don't know if you guys can hear me.
Sorry.
What did
That
you
was
say, Mateo?
exactly my point. Yeah, that was exactly my point. That this
So-
last equation you wrote could, captures the average fidelity, right?
Yeah, so he's saying that the distribution at this point of, you have not yet put anything about the distributions of the DIs. Well, I mean, this whole up until this last step. So if for some funny reason you decided to swap after one step that you knew that you were successful or some weird thing, you just have to compute the new distribution.
So one could, for example, add like a +1 here, for example, to capture that. Oh, it's a little bit delayed.
Yeah, I don't know why you would do anything other than swap ACP unless you're doing distillation or.
Yeah, it just is a little bit slow, it seems, the iPad. Yeah, so I guess one could make it more general, but in practice, one would always do swap ASAP, at least when you're looking at the case where you don't do any distillation. Okay, so we have this new quantity, ZNT, where we had this new, this free variable T. The nice thing about this is that it allows us to write Zn plus 1 T in terms of the smaller ZNT. Let me put here ZNT prime. What I'm going to do now is sum over T prime, ranging from 1 to infinity. And let me just write it down, and hopefully intuitively becomes clear what is happening. The intuition behind this is that this guy tells us, okay, how does that n look like? But when we fix the last link to be equal to T prime. If we now add another link that succeeds at time T, well, then the additional decoherence factor is given by this guy here. And the probability that the the last link will succeed at time T is given by this guy here.
What is the T in that superscript? Is that a vector?
So no, this T is really just if I look at this definition here, I say, okay, sum over all instances, but for the last link, you should only sum only over those sequences that have the last link at T.
At T, okay. I see. So now Zn plus 1 T is now Tn plus 1 is T. By that recursive definition.
Yeah. Yeah.
I see. So you just take the definition of that. You can take the Q to the Tn plus 1 out, which is Q to big T. And one extra term on lambda that will be minus T prime. I see.
Yeah.
Yeah.
So this already gives a recursive formulation. So one could, in principle, put this in Mathematica or something like that and evaluate this. But it turns out there's an even nicer way of looking at this. So let me first make a statement that I won't prove, but for any n, ZNT is always of the following form. It's a sum over A and B, where A and B are just positive integers. KAB is some real numbers, so coefficients. And here I always have something of the form, the following form. Oh, sorry, this should be Q.
So this is an ansatz.
No, so one can prove this, but I won't prove this now for this long. If you go through the recursion steps, you can prove this. So let me slightly rewrite this to make it a bit more, I guess, quantum info friendly, and then it will be hopefully a bit clearer what will happen. Oops. I am just going to replace, or just going to define a vector AB, and it's really this AB is just defined as Q to the power AT. Just looking at that. The reason why I'm doing this is that I can think of this transformation that takes me from ZNT to Zn plus 1T. This map is really a linear map on the vector space V that's given by the span of all these guys, all these vectors A, B's. So in general, my Z and T will always be a linear combination, will be an element of this vector space. And applying this recursion step is just applying a linear transformation on this space. So you don't even have to go really to solving this. You don't have to do this recursion step every time. We can really just think of as, well, applying a linear map n times. And so to maybe make that explicit, m applied to a b would just be equal to some coefficient that only depends on a and b. Then we get some new vector a plus 1 comma b. And then we get some other term d a b, which again just only depends on, this is coefficient that only depends on a and b. And then we here get 1, 1. So this gives us our new vector. We can again apply m to this very simply, again apply m, and this allows us to purely in linear algebra terms by this recursion step. Then finally, after we did,
Remind me, what is AB? I mean,
yes. So the vector AB is just shorthand notation for the following.
A dot T. So T is the not the full vector from T1 to T.
No, T is the free variable here.
For P is that the scalar.
Yeah. Or it's a free variable in this case.
Yeah, yeah.
And so these guys are all linearly independent for different A and Bs. Or I can think of them as formal linear combinations of these guys.
So it's just a number like this AB.
So T is a free variable, so it's allowed to change. So this will be some function.
So it's a function of T.
Yeah.
Yeah, I was just confused writing it like a cat. So it's but it's not a vector.
So you can think of it as a vector. So I don't even have to think of it as a function. So it basically boils down to this following idea. Z and T, I can always write as a linear combination of these guys.
Yes.
Or better said, as these guys. So I can think of it as an element in some vector space.
What does A and B run over the summation?
Over all positive integers.
That's what it's, okay, now I see this. So it's a matrix multiplication. That's right. Okay. Yeah. So you can just multiply that matrix. So that matrix multiplication is that M operator.
Exactly. Yeah.
Okay.
So the problem is that M is infinite.
It's infinite by infinite matrix. Yeah.
Yeah. But one can just think of this as this step here as a replacement rule.
Got it. Yeah. Yeah.
So maybe I can fill this. Let's see. Let me quickly show this on my screen. Hopefully nothing embarrassing will pop up. So for example, if you want to implement some Mathematica, it's really just these lines here. I've defined these coefficients here. And now I won't go into details, but I'm just applying this replacement rule every time. So in just these few lines, I can analytically calculate these small things. I should say, I should have explained this before. Let me try to just explain this without the iPad. I can also generalize this approach to the case of a cutoff. The idea of a cutoff is that you impose some condition where you're going to say, okay, if I reach this condition, I'm going to throw away all my entanglement and start over again. Why would you want to do this? Well, maybe at a certain point you realize, hey, my entanglement is very, very bad. I'm not going to use it for anything. The fidelity is very low, so I might as well just throw it away and start over. One type of cutoff that you can consider is you say, I'm going to, as soon as I am going to attempt elementary link generation, I'm going to start a timer. And I'm only going to allow, I only want to succeed within, say, 5 rounds. If I don't succeed within 5 rounds, I'm going to abort and start over again. And so one can change this cutoff parameter, such as to optimize, for example, the secret key rate or some other quantity of interest. I won't go into detail here, but one can generalize the previous analytical approach also to the case of a global cutoff. And that's what these functions do here. So let's, I'm going to show you the analytical expression for 6 links for the case of the global cutoff. And then we get this beautiful, beautiful expression. You know, sometimes mathematics is just pure beauty. It's, yeah.
Looks familiar.
Yeah.
So it still keeps going actually for a bit. So maybe, of course, maybe one could still simplify this a bit with Mathematica, but the key point is that, you know, I just press the button and I Mathematica.
And this is because of your recursive relation.
Recursive relation, yeah.
We're almost there. There we go.
Not too bad.
Not
If
too
we
bad.
scroll.
Yeah. And so what this allows us to do is we can now say, okay, well, we can change this cutoff parameter and see what is the result of secret key rate. So here on this plot, I have the cutoff on the x-axis, and on the y-axis, I have the secret key rate.
So you're using the usual 1 - 2 binary entropy.
Yeah. Yeah, in previous projects, I used a little more complicated stuff like the state stuff, but
That's fine. That's
it's
too
formats,
easy.
yeah. And so here for several different parameters, for several values of the success probability P and the lambda parameter, I show the secret key rate as a function of this cutoff. Well, you can see that already in cases, you know, in a case where you have no cutoff, which is basically here, you can tune your cutoff to basically get a 4-fold increase in the secret key rate. And in actually a lot of cases, you need a cutoff to actually generate any secret key at all.
The cutoff units are how many time steps you wait maximum?
Yeah. So normally you would have to do like Monte Carlo simulations or maybe try to estimate this somehow, but nowadays you can do it analytically. The expressions are maybe not so simple, but at least it's analytically.
Wait, so the x-axis is that cutoff?
Yeah.
The other thing that you said about getting some weight at all, what do you mean?
So for example, the case of no cutoff corresponds to going to taking the cutoff to infinity.
Oh.
So, you know, here I already see that I don't have any secret key rate. So I need to be in this regime to actually generate any secret key at all.
So by waiting too much, I'm getting such low fidelity that I don't have any secret keys.
Yeah.
Right.
And so, of course, if you lower this cutoff, you might have to restart quite often, but that's better than not being able to generate any key at all.
Ah, I see. Okay. The top curve has a different p value. I was wondering why that. Right?
Yeah. So the cutoff is different for different p values. One.
And also the steady state behavior or like the no cutoff behavior.
So is it like if your end-to-end fidelity drops below that 81% value, you drop the link?
Well, so that is sort of intuitively what you're doing, but here the cutoff is only on the, I only say the sort of the nodes, they don't allow for communication between themselves. Otherwise, they could decide, hey, now the fidelity is below 0.81.
Yeah, because it's ASAP swap, so yeah.
But here I'm saying, okay, the nodes, they're only keeping track of how many rounds they've been waiting for. So they cannot go into, they cannot look at how their state looks like.
Yeah,
But it's a rule book. Everybody knows that's the cutoff.
yeah, but so in the end, I guess Alice and Bob, once they perform their measurements, would know that the fidelity was below 81%.
Yeah.
And that's when you drop.
Yeah.
So basically, the thing is that your fidelity is below 81%. So for next thing.
Your RCI.
Yeah.
That's one. Okay, that's very interesting. Do you know which way your cutoff will go with as a function of P and lambda?
So I am working on a few, one can do some like Taylor series expansion to get some idea of the parameter regimes. I don't know from the top of my head.
I'm even curious if you did a 3D plot with P here, lambda here, and the optimal cutoff here. What will that?
Okay, so I don't have it for the cutoff. I do have some plots where I should look at, okay, if I optimize over the cutoff and I change the lambda and the P parameter, what changes? Like how high can the secret key be? Yep.
So your expression with the sum of absolute value differences reminded me of something from our work on time multiplicators, where we were able to,
Yeah, we
I
have
think,
that
a bound.
Yeah, exactly.
We were able to bound this with some average values of an order statistic.
Yeah.
I was wondering if that would be a nice proxy without having to do this to get a good sense of the landscape of how that goes.
Yes. So some of the bounds I've been working on are exactly that. You can use Jensen's inequality to just look at the distribution of the absolute value differences. And it actually gives quite good approximations.
Because the order statistics there are quite easy to complete.
Yeah. Way easier.
They're obscure, but quite easy to complete.
Another thing I was wondering, so in this paper that Pradeep and Ashlesha worked on, we found some scaling laws for basically swap ASAP like repeaters, but with a twist that you wait for a certain number of successes before you decide that you want to swap every node.
Okay.
But we didn't account for any fidelity. So our links were perfect fidelity. But we did account for losses. And turns out that there's a you switch between having sub-exponential and exponential scaling with distance. As you be switching losses when you're deciding which qubits to swap on in the repeater among those block of potential successes that you have waited for. So I was wondering if you bring in fidelity, and can we do any scaling law calculation for swap ASAP repeaters with time multiplexing?
I think there is a proxy answer to that in the follow-on that Kaushik and I did, because there we brought in infidelity due to imperfect trap diagonals and whatnot, but those are very, platform specific numbers. We never.
But even there, I don't think we did quite so what we did there was account for fidelity, what I'm saying.
But we introduced the cutoff in the sense by saying that, hey, up to this time, we know our qubit is pretty much fidelity 1.
Yes.
After this, drop it.
Just drop it.
Which is akin to like a very high fidelity target and putting a sharp cutoff in Kenneth's thing. But yeah, I agree. Kenneth's model would be more general, but.
Yeah, I'm saying that if, let's say, we take Kenneth's model as is, even without time multiplexing, if we say that we allow the protocol to pick the optimal cutoff for the given P and lambda between Alice and Bob as a function of the total distance, if I were to allow myself to put the optimal number of repeated nodes, I optimize over n also. How does my rate scale with the distance between Alice and Bob? Is that exponential? Is that sub-exponential? Does that beat the repeaterless performance bound? What P and lambda need to be to beat the repeaterless performance bound? That kind of a study is what I'm thinking. And then if you bring in time multiplexing, that would be another.
This is time multiplexing in a way, right?
No, it is not quite. So we are
This is time multiplexing without any space multiplexing, really.
We are not quite time multiplexing. So you're waiting for the first success. Well, I mean, Pradeep is right. I mean, you
want one success and M attempts.
It's like time multiplexing without having a predetermined time multiplexing block. You're just waiting until you get a success on the left and success on the right, and then you swap. So your effective multiplexing block length will not be predetermined. It's determined by when the end-to-end, the first success end-to-end happens, and then everybody starts again. So yeah, it will be interesting to see if we can get a scaling law for the rate distance trade-off. So this is probably going to be the first thing one would implement. I mean, before distillation or anything.
I do fear that because now your latency is accounted for in your attempt rate, you're going to take a hit there. But I think it's also a trade-off of how long your qubits are versus. Yeah, I don't. But specifically
So as you increase n, meaning the number of repeaters, your latency will decrease, which will increase your rate. So there will be this another factor that will boost up the rate artificially, or not artificially, but
Sure, because
you're also wanting more successes, so you need to.
Also, you're taking hit from DSM.
from DSM. So
If you increase.
but DSM right now there is no noise, but we could do what Nitin was suggesting.
But fidelity drops, right?
So like a q to the
Oh,
power
you're
n
right,
minus
you're right,
1 will
you're right.
become.
Yeah. No, there's no Q here. There's
No, so not q. I was saying the overall hit due to the number of swaps.
Yeah, it has nothing to do with success, probably.
Yeah.
So it's what Ashlesha is saying is that the fidelity drops with the number of swaps. So that's
Basically, you lambda to the power n.
exactly. Yeah. So it's not clear. So that will be an interesting optimization. But this is a good calculation for a near-term repeater because you're assuming you just have single memories. So your time step really is driven by the latency. So if you deploy repeaters more frequently, then your effective time step also decreases. Your rate goes up, but you have more swaps, your rate goes down because of the fidelity decrease. So where does it play out? If you work on the full rate versus distance envelope, where every total distance between Alice and Bob, number of repeaters has been optimized, what does that whole plot look like? As a function of just your raw parameters, which is P and lambda. That's it. So
one thing I've also been looking at is if you do include noisy state generation, you can have more repeaters, but you get hit more often by this noisy state
by
generation.
the noisy state
So there's
generation.
also a bit of interesting trade-off there. Let me maybe quickly, well, I don't want to go over time. I still wanted to talk about the numerical approach, but
I think we may not have the room. That's
okay.
I am on a meeting that is supposed to happen here right now. Are you? No, this is the, no, you're not. MPLC lab meeting, this is probably when you are.
So that might be Dal's studio.
No, this is not our student. This is a meeting with Amherst group, but you're meeting here.
Well, in that case, let me maybe close with the thing I would like to discuss. If you're interested in hearing more, please come drop by. I basically said that we wanted to calculate the Zn, and I used the term Z, symbol Zn, for a specific reason. Turns out, if one squints your eyes a bit, one can really show that this is a so-called partition function. Let me write this out. A partition function, and I mean that in the sense of statistical physics. Partition function of a system that models film growth. Unfortunately, I don't really have time to explain that now. But what this really tells you is that, well, again, I don't have the time, but a lot of people, smart people, have thought how to calculate these partition functions for general systems. And so we can actually use a lot of these tools from statistical mechanics to calculate the Zn. There's very much a sketch of what I wanted to talk about. But
so where does that partition function show up?
so if you look at this function here,
Oh, that's it. I see.
I can reparameterize this, and then it looks something like this.
So you're saying that to bound the performance, you can borrow from the literature on partition functions.
Yeah. And in particular, there's now a sort of system associated with this sum here, where the energy is given by this thing in the exponent.
Yeah.
Oh, well, sorry. I guess you guys cannot see it. And this really corresponds to a one-dimensional chain in statistical physics.
Yeah.
One can use, for example, the transfer matrix approach to calculate this. That is very briefly what I wanted to talk about.
That is accurate for large ends or for any end.
So normally in statistical physics, you're interested in the thermodynamic limit. The transfer matrix approach also, you can still do in the finite case. Yeah.
Does this analogy still hold for two-dimensional?
Yeah, so that's a good point. I've been thinking about generalizing some of this stuff.
Those 2D icing models, calculating these partition functions can be challenging in itself, and that's a whole area of research in statistical thermodynamics.
Yeah. So maybe we should go to higher dimensions where it's easier.
Well, or maybe the quantum network could be a tool to calculate those pure partition functions.
Perhaps. So maybe
You
Solve a hard problem with a harder solution.
well, yeah, maybe we could talk about it, but I think for 2D it becomes a bit harder. I have some ideas of generalizing this to a G set distribution where I look at not really two-dimensional systems, but it's not really clear if their statistical mechanics helps.
Nice.
Nice talking. All right, if there's no questions, then maybe let's close here.
Yeah, thank you very much. So we're both are meeting there, not here yet. I'm going to get Kenneth. I'll get you access to that room. Let's go.